Welcome back. So I apologize, I was a little emotional there at the end of the video, but this is something that is very important to me personally. When people look at logarithmic scales and not appreciate the scope and, pardon the pun here, the magnitude of how serious just a one or two difference can make on a scale like Richter scale or hurricane scales or other sorts of scales that are logarithmic in nature. So there are several different logarithmic scales out there, not just the Richter scale. But in general, just like how we had a common growth formula here, there's also a common logarithmic scale formula. And it's going to be the logarithm of some ratio. You take the magnitude of whatever event you've got, or the intensity of whatever, you take the intensity of the event you are observing, and you divide by whatever you consider to be a significant event. And that ratio you then plug into your logarithm, and that gives you the magnitude for your event. And so that's how earthquakes are measured in terms of magnitude. It's also how sounds are measured. And don't quote me on this because I might not remember entirely, but I think either tornadoes or hurricanes or one of those, maybe both, also use a similar scale. But let's talk about sound a little bit. The famous-ish Bell scale does this as well. But really, its more popular cousin, the decibel or 10 bell scale, is a little more popular. So the decibel scale uses that same ratio, but they multiply that log by 10. And that's kind of nice because remember, this log is base 10. And so when you go up by 1, that means you go up by a factor of 10. Well, in multiplying decibels by 10, I now see that I go up by 10 decibels. I am 10 times louder. That's the handy piece there. Also, I'm going to go ahead and tell you this. The I0, the threshold of significance, in my engineering days, we always did watts per square meter, 1 times 10 to the negative 12. For whatever reason, your author really loves watts per square centimeter, so I've got that there too. But whatever number you need to use, just pick the one where the units agree. For example, suppose we're watching a rocket take off, and we want to know how loud it is. Well, in decibels specifically. So I have some intensity here in watts per square centimeter. I want to know what this is in decibels. So I am going to take the formula, plug in my intensity value, which I just had, divide by the threshold, again in watts per square centimeter, divide through, and this is something that your calculator is going to, well, you don't need it for this because they're dividing by 1 and then the exponents. But anyway, you run this through a calculator, you get 114 decibels, and you're done with the problem. But here's the follow-up question. Is that okay? I do this in pretty much every class that I teach, but let's talk about safety. How loud is loud? Because the human ear, I don't know if you've realized this or not, can hear a ridiculous variety of sounds at a ridiculous amount of intensities, ranging from super duper quiet to, of course, super duper loud. So the threshold of human hearing, the faintest hearable sound, has some intensity associated with it. Of course, there are quieter things. You can Google anechoic chamber, be a fun rabbit hole to fall into. There are quieter things, quieter places. But also, we can do louder, right? Just sitting outside at a still countryside, you can still hear things, be it the wind or just the air moving around you. Sitting in a quiet room, of course, you got electricity, you got the air conditioner, and that's now 10,000 times louder than the faintest observable sound for humans. 100 times louder than that is normal conversation. 100 times louder than that is shouting or traffic. 10 times louder than traffic and shouting is headphones. And I want you to notice something. We go from, oh yeah, no problem at all, to 8 hours, to less than an hour, to 5 minutes, to a few seconds, to nope, not at all.